Today we're going to discuss nozzle divergence angle in a conical nozzle and how it's a correction factor to the exhaust velocity. In a previous video we described the exhaust velocity as being given by 2 times the mass defect alpha times the burn-up fraction phi to the power of a half times by c. But in reality we must multiply this by a further factor called lambda d, which is our nozzle divergence term. Without this, the exhaust velocity is an approximation, and this is an important factor we have to consider. So let's imagine we have some engine nozzle, and it's a conical shape design, and it's given a length of L0, and there is material coming out the back, and this produces a well collimated beam. This is an ideal rocket scenario. In reality, a rocket nozzle would not perform so ideal, and so we have to take account of that. So here's our nozzle design again. This time we have a divergence of the beam, so it's no longer well collimated. This half angle here we call theta, and by definition this whole full angle will be 2 theta. In the full equation, lambda d is given by 1/2 1 plus the cosine of the half angle. Okay, so lambda d is a correction factor to the nozzle exit momentum. Let us consider the 2 scenarios of, first of all, no divergence and then large divergence. So no divergence. In this scenario we have an efficient axial jet. And this implies a high exhaust velocity and therefore high specific impulse. So we want the beam to be as well collimated as possible. But this tends to require a longer nozzle design, which is our L0, which implies an increase in mass. In the other scenario of a large divergence, we have a less efficient jet, which implies a lower exhaust velocity and therefore lower specific impulse. But the good news is, if we call this length here L1, it requires a shorter nozzle. Therefore L1 is less than L0. And this implies lower mass. So as you can see, we're talking here about a trade between mass versus performance. Do you want high efficiency for high exhaust velocity, which means very low collimation, but it also means increased mass on the system? Or will you be happy instead with a less efficient performance for low exhaust velocity, larger divergence on the beam, but this would require a lower mass in terms of the nozzle itself. Let's consider the scenarios of plotting the burnout fraction phi as a function of the exhaust velocity, and if we were to plot this for 0 nozzle divergence, it might look something like this. If we were to go to 15 degrees divergence, it sort of looks like this, and then for a very large divergence of say 30 degrees, it might be here. So we can see that a perfectly collimated jet has no divergence and is what we call an ideal rocket. And in this scenario, lambda d is equal to 1. Now, if we think about our equation for the nozzle divergence, lambda d equals 1/2 1 plus cos theta. The scenario where theta is equal to 0 degrees, the cosine of 0 degrees is equal to 1. In which case, this whole term goes to 1/2 1 plus 1, which is equal to 1. So an ideal rocket, lambda equals 1. This is a perfectly collimated jet with no divergence. Now let's consider the other two scenarios we looked at, 15 degrees and 30 degrees. So for theta equals 15 degrees, we have lambda d is equal to 1/2 1 plus the cos of 15, which comes out as 1/2 1 plus 0.9659 is equal to 0.9829. So it's 98.29% essentially. And if we consider a scenario of theta equals 30 degrees, lambda d is equal to 1/2 1 plus the cos of 30, which is equal to 1/2 1 plus 0.866, which is equal to 0.933, or 93.3%. And then if we take the scenario of a deuterium helium-3 reaction where alpha is 0.0039, that's deuterium helium-3, and we assume a phi burnup fraction of 0.1, 10%, and we know the exhaust velocity is given by 2 times 0.0039 times by 0.1 to the power of a half, which will be 0.0279 C, or approximately equal to 8,373 kilometers per second. So this is without the correction factor. So now we want to see how this looks with the correction factor for these different values of theta. So let's make a little table. We have theta here, and we've got 0 degrees, 15 degrees, and 30 degrees. So 2 theta will be 0 degrees, 30 degrees, and 60 degrees. The nozzle divergence, when we calculate it, comes out as 1.0, 0.9829, and 0.933. And then if we calculated the exhaust velocity in kilometers per second, we already know the first one, which is 8373. For the 15 degrees half angle, it comes out as 8229, and then for the 30 degrees half angle, much larger beam divergence, 7812. So that's really interesting. Now there's a further factor which we need to think about, which is something called the jet efficiency. The jet efficiency, we notate it with E to J, and essentially the nozzle divergence angle is given as a function of E to J, the square root of that, which of course therefore implies E to J is equal to lambda d squared. So if we calculate that, we end up with jet efficiencies of 100. I'm going to calculate it as a percentage, which is a useful way to express it. For a 15 degrees half angle, it comes out as 96.6, and for the 30 degrees half angle, it comes out as 87.05. So we can see that a much larger divergence of the beam gives rise to a poorer jet efficiency. Now, since we know that lambda d is equal to e to j to the power of a half, we can rewrite our exhaust velocity expression to alpha phi to the half times by c times by lambda d, and then we can also write it as exhaust velocity is equal to 2 alpha phi to the power of a half times by c times by e to j to the power of a half, or to simplify it even more, exhaust velocity is equal to 2 alpha phi e to j to the half times by c. So what we can see here is that the exhaust velocity is now given more accurately as a function of 3 parameters. The first is the mass defect, which defines how much energy can possibly come out of the thermonuclear fuel. Phi, which is the burn-up fraction, which defines how well you have compressed up that fuel and got the maximum energy out of it through that process. What's the efficiency of that explosion? And E to J, which is our jet efficiency, which is related to our nozzle divergence term, and this is an efficiency on the whole operation. And I think it's important to consider what that means. So actually, we can define the jet efficiency as being equal to the power of the jet divided by the output power. That is to say, the power in the exit nozzle of the jet divided by the power produced in the thrust chamber. So therefore, we can also say that 1 minus e to j is equal to the losses. And these losses are mostly made up of two factors, which is the power of neutrons and the power of X-rays. So 1 minus e to j is equal to power of the neutrons, power of the X-rays, or to write it differently, e to j is equal to 1 minus the power of the neutrons plus the power of the X-rays. So when we say that we have a 87% jet efficiency with a 30% divergence angle in the nozzle, that means by implication 13% of our energy is being lost in this process of converting the power in the thrust chamber to the power that's in the exit nozzle. And a good design will optimize the power cycle for maximum jet efficiency and minimum radiation losses. That's it.